Well, funny seeing you here. Welcome back to another episode of Maths. Thanks for taking the time to join me today. I hope you're doing all right. And today we're going to be delving into kind of an interesting math topic that uses a lot of the stuff we've been using so far. This whole unit's been pretty connected. We've kind of seen that prime factorization is like the key here. Everything boils down to the prime factorizations of numbers because, well, primes are the atoms that make up numbers, right? We've discussed this before, so everything from greatest common factor to lowest common multiple to primes, coprimes, all that stuff, it's all primes. And hopefully through these videos, you're starting to get a deeper appreciation for what numbers actually are and how they go deeper than just being an amount of things, but they're kind of structured things that are based off of prime numbers, and we can use that structure in order to compare numbers and do all sorts of cool applications with them. So we're getting really close to finishing up this segment of the Fundamentals of Algebra series. The checkpoint will be coming pretty soon. Still got a couple of videos. But today we are going to be discussing divisibility. So way back several videos ago, we discussed divisibility rules, and we did the divisibility rules for 2, 3, 5, 9, and 10. So pause the video now, see if you still remember those rules. To be divisible by 2, it had to be an even number. So for example, 10 was divisible, but 13 was not divisible by 2 because, well, 10 is even and 13 is odd. For 3 here, to be divisible by 3, the sum of the digits had to be a multiple of 3. So for example, 111 is divisible by 3 since 1 plus 1 plus 1 is 3, which is a multiple of 3. But 113 would not be a multiple of 3 because 1 plus 1 plus 3 is 5, which isn't a multiple of 3. All right, for 5, it had to end in a 0 or a 5. So 35 would be a multiple of 5, but 37 would not because it doesn't end in a 5. And for 9, kind of like with 3, the sum of digits had to be a multiple of 9. So, for example, we know that 108 would be divisible by 9 since 1 plus 0 plus 8 is 9, which is a multiple of 9. But the number 134 would not be since 1 plus 3 plus 4 is 8, which is not a multiple of 9. So that's a way we can check for divisibility by 9. And lastly, if it was divisible by 10, the number had to end in a 0. So 30 is divisible by 10, but the number 4023 is not since it doesn't end in a 0. So that's just a quick recap. Feel free to go back and rewatch that video if you found you weren't super comfortable or familiar with any of these. So now what I'm going to do is we're going to discuss some divisibility rules for other numbers, but you're going to see that there's kind of a deeper logic to what's going on here, and we're going to eventually find that we can make our own divisibility rules for all sorts of numbers. You won't just have to kind of memorize rules that are given to you, you can actually kind of create your own rules using the structure of these numbers. So the idea is we're going to kind of break the number down, see what kind of makes up the number, and then use that to figure out its divisibility rules. So we'll start with the divisibility rule for 6. All right, so we know that 6 is 2 times 3, that's its prime factorization. And since 6 equals 2 times 3, that means that 6 is divisible by 2. And it also means that 6 is divisible by 3, right? So what we can do to make a divisibility rule for 6 is we can say then that a number is divisible by 6 if it's divisible by both 2 and 3. Right? Since 6 is divisible by 2 and it's divisible by 3, that's its prime factorization. A number is divisible by 6 if it's also divisible by 2 and 3. For example, the number 18, we know that is just 3 times 6, right? So 18 is divisible by 6, but we could check for that since 6, we know that that is going to be 2 times 3. So since 18 is divisible by 2 and divisible by 3, it has to be divisible by 6, right? Since, well, 2 times 3 will be in its factorization, which means that 6 is going to be a factor of 18, which means it's divisible by 6. So this is a way we can check to see if a number is divisible by 6, basically by using divisibility rules that we already know. So let's do another example. All right, so let's check if 1860 is divisible by 6. Well, all we have to do is check if it's divisible by 2, which it is because it's even. So even, so divisible by 2. And to check if it's divisible by 3, let's add its digits up. So we have 1 plus 8 plus 6 plus 0. That's 9 plus 6 plus 0. That's 15. 15 is a multiple of 3. So our number is divisible by 3. Since it's divisible by both 2 and by 3, our rule that we just learned up here tells us that 1860 is divisible by 6. So what we did is we found the divisibility rule by looking at its factorization and creating a new divisibility rule for it. So let's try another one. Let's look at the divisibility for 15. All right, so what's the factorization of 15? Well, 15, that is 3 times 5. So can you think of what a divisibility rule for 15 is going to be? When is a number going to be divisible by 15? Well, very similarly to 6, a number will be divisible by 15 if it's divisible by both 3 and by 5. If a number is divisible by 15, it has 15 as a factor of it, which means it has 3 and 5 as factors of it, which means it has to be divisible by both of them. So for example, we could look at the number, so we could look at this number, so 4,545. So to see if it's divisible by 15, we need to first check if it's divisible by 3, so we can do that by adding its digits. So 4 plus 5 is 9, plus 4 plus 5 is plus another 9, so that's going to be 18. 18 is a multiple of 3, so our number is divisible by 3. And our number ends in a 5, which means it's divisible by 5, right? It needs to end in either a 5 or a 0. That is satisfied, so is divisible by 5. Since this number is divisible by both 3 and by 5, it has to be divisible by 15. So this isn't too bad, right? We're just using divisibility rules we already know. We're looking for divisibility of some number. We're splitting it up into two smaller numbers whose divisibility rules that we already have, and then just testing to see if the number is divisible by those two pieces, which then makes it divisible by the greater part. Now, it's not always this simple. Let's say we wanted to make a divisibility rule for any number. Is it always going to be following this process? No. So one instance that will be different is if it's a prime number, right? So for example, if I want a divisibility rule for 7, we wouldn't really be able to use any of these because 7 is prime. It can't be factored into other pieces. So 7 would need its own unique divisibility rule, which we will cover someday. It's a little bit complicated for right now, but we will get there someday. But there is also some other instances where it's not as simple as this. Not just for primes, but for other composite numbers, we might not be able to just get such a simple divisibility rule by splitting it up into these two pieces. So let me show you what I mean. Alright, so now let's look at a divisibility rule for 18. Alright, so if we consider 18, we know that 18 is just 6 times 3, right? So we do our user rule process and we say that a number is divisible by 18 if it's divisible by both 6 and 3. And we have a way to determine if a number is divisible by 6 and by 3, right? We've learned both of those. So we should just be able to tell if a number is divisible by 18. So let's do an example. Let's take the number 24. Okay, well, 24, that's divisible by 6, right? 6 times 4 is 24, so 24 is divisible by 6. But 24 is also divisible by 3, right? Since 3 times 8 is 24. So both of these are covered, which means our number should be divisible by 18. But is 24 divisible by 18? No, right? 24 is not divisible by 18. If we take multiples of 18, we immediately skip over 24 when we go from 18 to 36. So we see that 24 is not divisible by 18, and yet this test is telling us that we are getting it's divisible by 18. So what that tells us is actually this test is wrong. So if this test is wrong, then how come we were able to use it for the other ones and it gave us correct answers, but we weren't able to use it in this situation? Well, if we consider 18 as 6 times 3, what is 6? 6 can actually be broken down further, right, into 2 times 3. So we can consider 18 as 6 times 3, which 6 can be written as 2 times 3, times 3 like that. So we have 18's prime factorization here, and then I'm also going to write out 24's prime factorization. Alright, so we see that 24 has 2 times 3 in its prime factorization, which means it was divisible by 6, right? And that followed from 6's divisibility rule that it was divisible by both 2 and by 3. But then when we go to check if it's divisible by 3, we do see, yeah, it's divisible by 3 because, well, 3 is, of course, in 24's prime factorization. However, the divisible by 3 part that we wanted for 18 came from this 3 right here because we thought, well, it should be divisible by this 6 here and divisible by this 3 here, which then would make 18 in total. But the problem is we can't guarantee that if a number is divisible by 3, it's going to be for this 3. It could be very well for this 3, and we see that's the case for 24. The 3 here that makes up the factor of 6 for 24 is the same 3 that makes up the factor of 3 for 24. There's not multiple 3's here, so we see that 18 is not going to be something we can make in the prime factorization of 24. There's not a second 3 here. The problem of choosing this divisibility rule of saying it has to be divisible by 6 and by 3 is that 3 is a factor of 6. 3 and 6, they share a common factor of 3. And because of that, we cannot actually guarantee that we can keep these separate from each other. The 2 and 3 that made 24 divisible by 6 contained the same 3 that made it divisible by 3. It wasn't two separate 3's. So that meant we weren't actually getting a number that's divisible by 18. So the test will not actually guarantee we're getting something that is divisible by 18. So how can we actually go about fixing this test so we can look at if a number is divisible by 18? Well, the problem occurred because 6 and 3 had a common factor. So what we need to do is we need to split 18 up into two numbers that are coprime, right? Numbers that have no common factor. See, it's all coming together. We got coprimes in here now. It's kind of crazy. So what two numbers will multiply to 18 that are coprime? Well, we know that 18 is also 2 times 9. And 2 and 9 are completely coprime to each other. They have no common factors. So we can say now that a number is divisible by 18 if it is divisible by both 2 and 9. So we don't have to worry about any common factors overlapping for these. We can, because they are completely coprime with each other. So now we can actually test if 24 is divisible by 18. Well, 24 is divisible by 2 because it's even. But it is not divisible by 9. If we add up the digits, we get 6, not a multiple of 9. And if we count by 9s, we have 9, 18, 27. We skip over 24, right? So it is not divisible by 9. So it's not divisible by 18, which is what we expected. That's what we wanted. So we say that this rule works for 24. Let's try another one. All right, let's try 10,872. So if we add up these digits here, we get 1 plus 0 plus 8 plus 7 plus 2. That is 9 plus 7 is 16 plus 2 is 18. That's a multiple of 9, so it is divisible by 9. And it ends in a 2, so it is divisible by 2, right? It's even. So this number is divisible by 18. And we can feel confident in this because this divisibility test was made using coprime factors. And if we whip out our calculator for a second to actually verify that this is divisible by 18, we see that when we divide it, we get a whole number, so it's divisible. Now, let's try the divisibility rule for 30. So we can write 30 as 3 times 10. So 3 and 10 are coprime with each other, so we can reliably make a divisibility rule for this. So we can say then that a number is divisible by 30 if it's divisible by both 3 and 10. But you might notice that we could actually come up with another divisibility rule for 30. We could say that 30 is 5 times 6. 5 and 6 are also coprime with each other. So we could say then that a number is divisible by 30 if it's divisible by both 5 and by 6. Or you might notice that there's even another one we could do. 30 is the same thing as 2 times 15. 2 and 15 are also both coprime to each other. So if we know the divisibility rule for each of these, we could say a number is divisible by 13 if it's divisible by both 2 and by 15. So we see that we actually can have some options because we have several different pairs of factors of 30 that are coprime with each other. So we have different options to test if a number is divisible by 30 or not. So hopefully you're starting to kind of get the idea that we can use coprimes and we can use the factorizations of numbers to basically generate divisibility rules for that number. But let's try another situation because there's one more situation where it's going to be a little tricky. So you might notice in all of the small numbers we've looked at, we haven't touched the divisibility rule for 4 yet. So 4 is an interesting situation because when we look at its prime factorization, what do we get? Well, we get 2 times 2, right? So 2 and 2 are not coprime with each other because they share a common factor of 2. So there's actually no pairs of numbers that are coprime with each other other than 1 and 4, right? 1 times 4 is going to be 4, and 1 and 4 are coprime with each other, but that's not going to be useful because if we want to say a number is divisible by 4, saying that it's divisible by 4 and 1, that doesn't help us at all because we still need to know how to find if it's divisible by 4. So other than the kind of what we could call a trivial case, the only possible factorization for 4 is 2 times 2. But we can't just say the number is divisible by 2, because then that's only accounting for one of these 2's, right? The number 6 is divisible by 2, right? 6 divided by 2 is 3. But 6 is not divisible by 4, right? Counting by 4 is 4, 8, 12. We skip over 6. So we can't just say that the number is divisible by 2. But what we could say is we could say it's divisible by 2 twice, right? And then we're accounting for both of the 2's. So we can say then that a number is divisible by 4 if it's divisible by 2 twice. So what do I mean by this? Well, let's take the number 48, for example. So we can check if it's divisible by 2 first. So it is divisible by 2 since it is even. So divisible by 2. So that means we could divide the number by 2. So dividing by 2, we will get 48 divided by 2 is 24. And that is also divisible by 2 because it's even again. So since it's divisible by 2 different times, the number is divisible by 4. Now this is arguably a less satisfying divisibility rule because we actually have to do some division in order to check for 4's divisibility. Now in the next lecture video, I will show a more effective divisibility rule for 4, but I want to kind of keep with the theme of constructing our own divisibility rules for this video by using the factors of the number. So that's going to cover it for today. We discussed how to basically use the factorization of a number in order to find a divisibility rule for it. And we found that the essential thing was to split the number up into a pair of factors that were coprime with each other, right? Like 3 and 10, 5 and 6, because we found that if they weren't coprime to each other, then there would be some overlap that would result in a divisibility rule that wouldn't work all of the time. And then we also saw in a special case like 4, where it didn't have any non-trivial coprime factors, we had to basically kind of say that the number was divisible if it was divisible by that number multiple times. So 4 would be a number is divisible by 4 if it's divisible by 2 twice. So in the next video, we're going to do some practice and get comfortable creating our own divisibility rules. But until then, I encourage you to kind of just try and make up some divisibility rules for yourself. Take one of your favorite numbers and see if you can create a rule for it to test if other numbers are divisible by that number or not. Well, I hope you found this video interesting. Thanks for watching. Have a good one. Stay groovy, and I'll see you in that next video.